Good evening, everyone. We are Group 7. I am Matsari and my colleagues are Sanduchi, Siddhija and Ishani. Today we are here to present a research paper, Gradient-Based Learning Applied to Document Recognition. So let's go into the presentation. This research paper was written by these four authors and they presented it in 1998 in Proceedings of the IEEE Journal. So the main message of this paper is better pattern recognition systems can be built by relying more on automatic learning and less on hand design heuristics. In introduction, they have mentioned so many related things in detail. Since the time is limited, let's go through some most important facts in the introduction. Actually, why gradient-based learning is important? The general problem of minimizing a function with respect to a set of parameters is a big problem in computer science. But gradient-based learning draws on the fact that it is easier to minimize a reasonably small continuous function than a discrete function. Throughout the paper, there is a word called backpropagation. So what is backpropagation? The basic idea of backpropagation is that gradient can be computed efficiently by propagation from the output to the input. Then they have talked about learn real handwriting recognition systems and global trainable systems. One of the most typical problems in handwriting recognition is not only to recognize individual characters but also to separate out characters from their neighbors within the word or sentence, a process known as segmentation. The technique of doing that is called heuristic over segmentation. And in global trainable systems, they mention that most practical pattern recognition systems are composed of multiple modules. So those are the key facts extracted from the introduction. Let's move to the major part of this paper, convolutional neural networks for isolated character recognition. They discuss this in three parts. They are convolutional network, LeNet5 architecture, and loss function. So what is a convolutional neural network? Convolutional neural network is the standard form of neural network architecture for solving tasks associated with images. Solutions for tasks such as object detection, face detection, pose estimation, and more all have CNN architecture variants. Following figure shows you some examples of object detection, face detection, and pose estimation respectively. Convolutional networks combine three architectural ideas to ensure some degree of shift, scale, and distortion invariance. They are local receptive field, subsampling, and weight sharing. Figure 1 is an example for receptive field, and figure 2 is an example for subsampling. Okay, so next move to the LeNet5 architecture. LeNet5 CNN architecture is made up of 7 layers. The layer composition consists of 3 convolutional layers, 2 subsampling layers, and 2 fully connected layers. Following figure shows you the architecture of the LeNet5. The first layer is the input layer. This is generally not considered a layer of the network as nothing is learned in this layer. The input layer is built to take in 32 by 32 and these are the dimensions of images that are passed into the next layer. The official first layer, convolutional layer C1, has 6 feature maps. Each unit in each feature map is connected to a 5 by 5 neighborhood in the input. The size of the feature map is 28 by 28, which prevents connection from the input from falling off the boundary. Layer 2 is a subsampling layer with 6 feature maps of size 14 by 14. Each unit in each feature map is connected to a neighborhood in the corresponding feature map in C1. The 2 by 2 receptive fields are non-overlapping. Therefore, feature maps in S2 have half the number of rows and columns as feature maps in C1. Layer C3 is a convolutional layer with 16 feature maps. Each unit in each feature map is connected to several 5 by 5 neighborhoods at identical locations in a subset of S2's feature map. Following figure shows the set of S2 feature maps combined by each C3 feature maps. If we talk about layer S4 is a subsampling layer with 60 feature maps of size 5 by 5. Each unit in each feature map is connected to a 2 by 2 neighborhood in the corresponding feature map in C3 in a similar way as C1 and S2. Layer C5 is a convolutional layer with 120 feature maps. Each unit is connected to a 5 by 5 neighborhood on all 16 of S4's feature maps. And layer F6 final layer contains 84 units and is fully connected to C5. So that's how LeanNet 5 architecture works. Let's move to the third part, loss function. The loss function is one of the important components of neural networks. Loss is nothing but a prediction error of neural net. And the method to calculate the loss is called loss function. In simple word, the loss is used to calculate the gradients, and gradients are used to update the weights of the neural net. This is how a neural net is trained. The simplest output loss function that can be used with the above network is the maximum likelihood estimation criterion, which is in our case is equivalent to the minimum mean squared error. The criterion for a set of training sample is given by this equation. So here onwards, my colleague Sandushi will continue the rest of the presentation. Over to you, Sandushi.
Thank you, Vatsali. As the time is limited, I am not discussing all the points in the slides. I am only mentioning the important points. Let's talk about the database first. To train and test the system, they used modified NIST dataset which containing binary image of handwritten digits. In here, the modified NIST dataset is containing 60,000 patterns for training set and 10,000 patterns for test. Let's move to next slide. In this research, they used 3 versions of database. The first version was regular database. The second version was designated database. And in third version, the images were reduced to 16 by 16 pixels. This figure shows some example randomly picked from the test set. LeanNet 5. They trained several versions of LeanNet 5. The step size epsilon k is calculated by this equation. In here, mu is a hand-picked constant and they used 0.02 for that. HKK is an estimate of the second derivative of the loss function with respect to omega k. And neta is the global learning rate. Let's move more on results. There is a common phenomenon when overtraining occurs. The training error keeps decreasing over time, but the test error goes through the minimum and start increasing after a certain number of iterations. But as you see in this plot, it was not found here because the learning rate was kept relatively large. You can see that the test error rate stabilizes after around 10 iterations through the training set at 0.95% and 0.35% after 19 iterations. Let's talk about the training set size effects for the performance. They train the network with various sizes of examples. According to this plot, it is clear that even the specialized architectures such as LeanNet 5, more training data would improve the accuracy. Let's talk about the classifiers and results. Many various classifiers were trained and tested on the same database for comparison. Since the time is limited, I am not going to more detail on each classifier in here. I am only mentioning the error rates for the comparison, and at last I will present the comparison chart of all classifiers. Linear classifier is a simple classifier and it gave 12% error rate on regular data and 8.4% on designated data. The next classifier is baseline nearest neighbor classifier. This is a k-nearest neighbor classifier and the error rate on regular data set was 5% and on designated images was 2.4% when k equals 3. Let's look at the principal component analysis polynomial classifier. As you see in this table, it gave 3.3 error rate on regular data. The next one is radial basic function network. And it gave 3.6 error rate on regular data. The next one is one hidden layer fully connected multi-layer neural network, and it gave the lesser error rate 1.6 on desalinated images with 300 hidden units. Next classifier is two hidden layer fully connected multi-layer neural network with having the lesser error rate 2.45%. LeNet 1 is the next classifier and it has the error rate 1.7%. And the next classifier is LeNet 4 with test error rate 1.1%. Next one is boosted LeNet 4. In here, three LeNets are combined. First one is trained as usual way. The second one is trained on the patterns filtered by the first net. And the third net is trained on new patterns which are disagree from first and second nets. This method has the test error of 0.7%. Next classifier is tangent distant classifier with 1.1 test error rate. Next, support vector machine. From the SVM techniques, modified VSVM has the lesser error rate 0.8%. Let's move to the discussion. The error rate on the test set for various classification methods are shown in this figure. As you see in this figure, boosted LeNet 4 gives the best performance with lowest error rate 0.7 on test data. When considering the rejection performance, patterns are rejected when the values of the corresponding output is smaller than a predefined threshold. In many applications, rejection performance is a more significant than raw error rate. As you see in this plot, again boosted LeNet 4 has the best performance, and when talking about the memory requirement, most of method require 1 byte and nearest neighbor method require 4 bits per pixel. Next, talk about importance of noise resistance. In the experiment described above, the importance of noise resistance and distortion invariance is not obvious in this case. And let's move to the next slide. Why would we want to train system composed of multiple heterogeneous modules? The answer is that the large and complex trainable systems need to be built out of simple specialized modules. The simplest example is LeNet 5, which is described previously. And when talking about the object-oriented programming, offers a way of implementing multi-module systems. Each module is an instance of a class, and module classes have forward and backward propagation methods, and they have the duality property. The software environment used in this research is to get the result is SN 3.1. When talking about special modules, multiplexer is a special case and min module is also an interesting case. Graph transformer networks designed much more easily and quickly by viewing the system as a network of modules. This module will describe in upcoming slides. My friend Dilhani will continue the presentation.
Thank you, Sandashi. Now we will talk about multiple object recognition. When considering this research paper, one of the most difficult problems of handwritten recognition is to recognize not just isolated characters, and they need to strings of characters such as identify strings of characters such as zip codes, check amounts or words. because most recognizers can only deal with one character at a time, we must first segment the string into individual character images. So now I'm going to describe in detail simple example of graph transformer network to address the problem we are discussing. So first one is segmentation graph. So it is a classical method for segmentation and recognition. Basically, this is called as heuristic over segmentation. This avoids making hard decisions about the segmenting by taking the large number of different segmentations into the consideration. So in here, the idea is to use heuristic image processing techniques that will find the candidate cuts of the word or string, and they use the recognizer to score the alternative segmentations thereby generated. So in the figure shown in here, you can see a number of candidate cuts are generated. Good candidate locations for cut can be found by locating minima in the vertical projection profile. So after that, the cuts have been generated. Alternative segmentations are best represented by the graph. It is called the segmentation graph. It is actually a directed acyclic graph with a start node and end node. And also each internal node is associated with the candidate cut produced by the segmentation algorithm. So now we will move on to the recognition transformer and the Viterbi transformer section. So as here you can see in the right corner a simple graph transformer network recognizer character is shown. It is composed of graph transformer called recognition transformer and Viterbi transformer. Here the goal is to goal of the recognition transformer is to generate a graph called interpretation graph, and it contains all the possible interpretation for all the possible segmentations of the input. In this case, the role of the Viterbi transformer is to extract the best interpretation from the interpretation graph. The recognition transformer takes the segmentation graph as input and applies this recognizer for simple characters to the images associated with each of the arcs in the segmentation graph. So here you can see in this figure, each arc is associated with its class label, and the penalty that the image belong to this class are produced by the recognizer. And the Viterbi transformer produce a graph with a single path, at least penalty in the interpretation graph. So in previous cases, we talk about the process of recognizing a string using heuristic over segmentation. And there we assume that the recognizer is trained so as to give a low penalties for the correct class label. So now here I'm going to talk about how to train the system at the string level to do the above thing without requiring manual labeling of a character segments. So this training will be performed with the graph transformer network, but in this architecture it is slightly different from recognition architecture. So in this paper they have mentioned 4 gradient based methods for training graph transformer based handwritten recognizers. They are actually at the string level, and they we can take it as Viterbi training, discriminative Viterbi training, forward training, and discriminative forward training. For the time being, I will describe few of them. Let's talk about Viterbi training. During recognitions, we select path in the interpretation graph that has the lowest penalty with the Viterbi algorithm, and the gradient of this loss function can be computed by backpropagation through the GTN architecture. This training architecture is almost identical to the previously taught recognition architecture, but the only difference is there is extra path, extra graph transformer called the path selector. It is inserted in between the interpretation graph and the Viterbi transformer. So this transformer takes the interpretation graph and desired label sequence as input, and then it extracts from the interpretation graph, and those paths contain the correct label sequence, and its output graph is called the interpretation graph. So now we will talk about the discriminative Viterbi training. The idea is here is not only to minimize the cumulative penalty of the lowest penalty path, but also to somehow increase the penalty of the competing and possibly incorrect paths. So this type of criterion is called discriminating because it plays the good answers against the bad ones. So our paper, they have also mentioned multiple object recognitions, space displacement neural network. For the time being, I'll skip this part and I'll hand over the presentation to my colleague Ishani. Over to you, Ishani.
Thank you, Sitija. Graph Transformer Networks and Transducers. Simply called GTN, it is a generalization of multi-layer, multimodule networks where the state information is represented as graphs instead of fixed size vectors. Both speech recognition and handwriting recognition have used gradient-based learning methods that integrate graph-based statistical models with acoustic recognition modules, mainly Gaussian mixture models and also neural networks. But the problem occurs is that there has been no proposal for a systematic approach to multi-layer graph-based trainable systems. The concept of weighted finite state transducers has been applied to speech recognition, handwriting recognition, and language translation. This has been mainly focused on efficient search algorithms and on the algebraic aspects of combining transducers and graphs. So, a different approach to graph-based trainable systems called input-output hidden Markov model was proposed in standard transaction. In this framework, the conversion operation takes acceptor graph and a transducer graph as inputs, and as the output, it builds an output acceptor graph. Each path in this output graph corresponds to one path in the input acceptor graph and one path and a corresponding pair of input to output sequence in the transducer graph. Considering an example for the compression of the recognition graph with the grammar graph, the methods check and fprop are used during the forward propagation. Gradients are backpropagated with the application of the method bprop. Two tokens that are on the start node of each graph can freely follow any arc labeled with the null input symbol and can be collected the corresponding sequence of output symbols along with the trajectory of the transducer token. In the real world, handwriting recognition and check reading system are the most useful in the incorporation of linguistic constraints when recognizing words or other character strings. Generalized transduction. The compression transformer object implements three methods. Check method is used to compress the data structure pointed to by arcs arc1 and arc2 and returns a boolean indicating whether corresponding arc should be created in the output graph. Prop method is called when check method returns true. This creates new arcs and nodes between up node and down node in the output graph and computes the information attached to these newly created arcs. bprop method is called during training and used in the frop call with the same arguments and compute the values attached to its output arcs. This is the pseudocode for a simplified generalized graph compression algorithm. It does not handle null transitions and does not check whether the token's trajectory is acceptable. The two main components appear in the pseudocode here. The SimToken recursive function, which is used for enumerating the token trajectories, and the associative array map, which is used for remembering which node of the composed graph have been visited. Notes on the graph structure. Now you have a basic idea of VPOP, check, and FROP methods. The structure of the graph depends on the nature of the graph transformer and the value of the parameters n on the input. This might be considered a combinatorial problem and not amenable to gradient-based learning. But the solution to this problem is to generate a large graph that contains the graph candidates as subgraphs. GTN Hidden Markov Model. GTN is a generalization and extension of HMMS by allowing to combine in a well-principled framework multiple levels of processing. As an example, Pereira and others have been using the transducer framework for stacking HMMS, representing different levels of processing in automatic speech recognition. In HMM, it has n number of nodes associated with the time step t and the state I in the model. The input-output HMM model is strongly related to graph transformers. It represents the conditional distribution of output sequences given input sequence. An online handwriting recognition system. Natural handwriting is often a mixture of different styles, lowercase printed, uppercase, and cursive. We have built a word recognition system which interacts with pen-based devices to recognize handwriting. It based on four main modules. They are preprocess, module, replicated convolutional neural network, and GTN. In this work, we have compared a system based on SDNN and heuristic over segmentation. Because of the sequential nature of the information in the pen trajectory, heuristic over segmentation can be very efficient in proposing candidate character cuts, especially with cursive. Considering the system flow, preprocessing reduces its intra-character variability, simplifying character recognition and design a map. In network architecture, it determines that the resolution was sufficient for representing handwritten characters. Then, in network training, keep the centers of the RBFS fixed and all the parameters, network weights, RBF centers were trained globally. Finally, do the experiments and evaluate results with high accuracy. The check reading system. The verification of the courtesy amount on a check is the task that is extremely time and money consuming for banks. There are mainly two steps. First, find the characters that are the most likely to contain the courtesy amount. Then, find the best interpretation of the amount using contextual knowledge represented by a stochastic grammar for check amounts. A GTN for check recognition, check amount recognition. Input for check reading system is a trivial graph with a single arc that carries the image of the whole check. There are mainly 5 steps: the field location transformer, the segmentation transformer, the recognition transformer, the confusion transformer, and finally Viterbi transformer and it returns a Viterbi answer. Gradient-based learning. The parameters of the field locator and the segmenter are initialized by hand, while the parameters of the neural network character recognizer are initialized by training on a database of pre-segmented and labeled characters. Rejecting low confidence checks. Checks can be rejected due to carry erroneous Viterbi answers. To minimize rejecting, rate them with the confidence and reject the check if the confidence is below a given threshold. This is the expression that is used to measure the confidence of the system. Results. Initially, nearly 5 lakh images of characters have trained from various origins spanning the entire printable ASCII set. On 646 business checks that were automatically categorized as machine printed, the performance was 82% correctly recognized checks, 1% errors, and 70% rejects. This can be compared to the performance of handwritten for the same test. 68 correct, 1% errors, and 31% rejects. Conclusion. In neural networks, backpropagation allows us to efficiently compute the gradients on the connections of the neural network with respect to a loss function. Handcrafted should be replaced by an automatic learn features. Large size systems can be learned by gradient-based methods with efficient backpropagation. This is the end of our presentation. Thank you all of you.